Imagine pressing play on the oldest home video in the universe. The screen doesn't show people or planets. It shows a single dim star so poor in heavy elements that it is almost pure Big Bang material. Before the Milky Way had arms, before our sun had dust to gather, this star had already lit its tiny flame. Tonight we go find it, read its chemistry like a diary, and ask a bold question. Can a star really be a time capsule from before our galaxy existed? Here's the idea that guides our whole journey. Right after the Big Bang, space made mostly hydrogen and helium, with a trace of lithium. Astronomers call anything heavier than that a metal, including carbon, oxygen, and iron. The first generations of stars forged those heavier elements and spread them when they died. So the less metal you see in a star, the earlier it must have formed. That is why metal-poor stars are cosmic antiques, and why finding one is like opening a sealed museum case. But we won't just say old and move on. We will do stellar archaeology. Think of an archaeologist brushing sand from an ancient pot. We do the same with starlight. Every element leaves thin, dark lines in a star's spectrum chemical fingerprints. By reading those fingerprints, we can tell which nuclear reactions ran in the past, and which kinds of supernovae seeded the gas before the star was born. In other words, chemistry is our clock. It tells us not just age, but ancestry. Why does this matter? Because the Milky Way did not appear all at once. It grew, merging with small galaxies, swallowing star clusters, building up its halo like a slow storm. If we can find a star that formed in the first few 100 million years after the Big Bang, we can watch that assembly process from the inside out. A single metal-poor star carries clues about when the first supernovae exploded, how violent they were, and where our galaxy's first building blocks came from. Let's set the scene in plain language. We're hunting stars that are dim, ancient, and chemically simple. Most live in the Milky Way's halo, the vast, faint sphere that surrounds the bright disk you see in night sky photos. They don't look special through a small telescope, but when we spread their light into a rainbow with a spectrograph, secrets pour out. Sometimes we find almost no iron at all, but a surprising amount of carbon or magnesium. That odd mix isn't random. It points to specific kinds of early supernovae and the physics inside them. You might ask, how can a star's age be measured if stars don't carry calendars? Great question. We have three main strategies. First, we estimate ages from how a star shines its temperature, brightness, and composition by comparing it to models of stellar evolution. Second, for a few rare stars, we use radioactive dating, measuring thorium and uranium and comparing them to stable elements, like carbon dating an artifact but with cosmic isotopes. Third, we trace the star's orbit to learn where it likely formed and how it migrated into the Milky Way. Over the next chapters, we'll meet a few record holders and ask what makes each one special. One famous target looks oddly young in the sky, bright enough for binoculars yet chemically ancient. Another hides deep in the halo, almost iron-free, a likely child of the very first supernovae. Each one tells part of the same origin story. The universe made its first heavy elements early, in just a few powerful deaths, and those elements set the stage for galaxies, planets, and eventually life to exist. We'll also demystify the jargon. When astronomers say population 3, they mean the very first stars, born from pure hydrogen and helium. We haven't caught one alive. They burned hot and died quickly, but we see their fingerprints in later stars. Population 2 are the next generation, metal-poor but long-lived. These are our fossils. Population I are modern, metal-rich stars, like the Sunday. The star we're chasing is a population 2 relic that remembers the violence of population 3. And no, metal-poor doesn't mean the star is weak or dying. Many of these stars are tough survivors. Some have been shining for more than 13 billion years. Their simple chemistry keeps them stable. Their orbits carry them far above and below the Milky Way's disk, where they spend most of their time in quiet space, untouched by the crowded lanes where stars like the Sun live. That isolation protected their chemical record for us to read today. Here's our promise. By the end of this episode, you'll be able to listen to a star's light and tell a story about how the universe built itself. You'll learn how a single odd ratio, like lots of carbon, almost no iron, can reveal the mass of a vanished first-generation star and the violence of its death. You'll see why some stars carry the chemical bruises of black hole birth, while others hold the soot of gentler, failed explosions. And you'll see how new telescopes and sky surveys are turning this treasure hunt into a map of our origins. So take a breath and look up. The spiral you know as the Milky Way is only the latest edit of a much older story. Somewhere in its dim halo is a survivor so primitive that it barely knows what iron is. In its light is a record of the first time the universe learned to build anything heavier than helium. Find that record, and you're not just looking at a star. You're opening a time capsule labeled Before the Milky Way. If you want to know how old a star is, first ask how dirty it is. Dirt, in astronomy, means metals, the heavy elements made after the Big Bang. The Sun is a messy teenager by this measure, rich in oxygen, carbon, silicon, and iron. Our quarry is the opposite. It is so metal poor that its surface reads like a near-pristine page from the young universe. That's the core trick of stellar archaeology. The fewer heavy elements a star has, the earlier it likely formed. Astronomers keep score with a simple code, Phi-H. It compares the iron abundance of a star to the Sun on a base 10 scale. A value of 1 means 10 times less iron than the Sun. 2 is 100 times less. 3 is 1,000 times less, and so on. When you hear extremely metal, poor, think Phi-H, below 3. Ultra is below 4. Hyper is below 5. Some rare stars push below 6 and even 7, which is like finding a library book that was shelved before the library existed. These numbers aren't fashion labels, they're timestamps. How do we find such ghosts in a galaxy with hundreds of billions of normal stars? We sift wide-field surveys, scan the sky, and look for weak traces of key lines, especially calcium's K-line near 393 nanometers. If that line is unusually faint for a star's color and brightness, metallicity might be very low. Catalogs from projects like SkyMapper, SDSS, LAMOST, and Gaia give us candidates. Then big telescopes with high-resolution spectrographs, Keck, VLT, Magellan, Subaru, split the light into thousands of razor-thin lines so we can read the chemistry in detail. It's a two-step hunt, broad net, then forensic lab. When we catch one, the spectrum can be shocking. Imagine almost no detectable iron, yet clear signals of carbon and magnesium. That odd recipe tells a story about a first-generation supernova that didn't explode cleanly. In mixing and fallback models, the early massive star detonates, outer layers rich in light elements escape, but much of the iron falls back into the newborn black hole. Gas polluted by that kind of event can form a second-generation star that is iron-starved but carbon-rich. If you've seen the label CEMP, carbon-enhanced metal, poor, that's what we're talking about. The CEMPNO subgroup, which lacks neutron capture enrichments, is often the purest fingerprint of those first asymmetric blasts. You might wonder about another dramatic type of early explosion, PAIR, instability supernovae, from supermassive, short-lived stars. Those should flood the gas with lots of iron and leave a distinctive, odd, even pattern in the elements. Curiously, that signature is rare in the metal, poor fossils we've found so far. That silence hints that the very first stars weren't dominated by those giant beasts, or at least that their debris didn't seed most of the gas that survived to make long-lived stars. The universe's earliest chemical factory seems to have been messy, lopsided, and selective. Fossils don't just live in the Milky Way's halo, they also hide in tiny satellite galaxies, the ultra-faint dwarfs, which are time capsules in their own right. With only a few thousand to a few million stars and very quiet star formation histories, these dwarfs preserve clean chemical records. One famous case showed an entire dwarf galaxy lit up with elements made by a single neutron star merger, proving that such events can dump our process material into small systems early on. Find a metal-poor star in such a galaxy, and you're not just aging a star, you're aging an entire family tree. A different clock sits in a handful of rare stars enriched in heavy R process elements like europium, thorium, and uranium. Those radioactive nuclei decay at known rates. By comparing how much thorium and uranium remain relative to stable neighbors, we can perform cosmic radiometric dating. No tree rings, no sand layers, just nuclear physics. When the math points to an age around the age of the universe, you're looking at one of the galaxy's oldest surviving citizens. Even a star's motion carries clues. Thanks to Gaia, we can trace orbits that swing far above and below the Milky Way's disk, plunging through the halo on elongated paths. Some trajectories tag a star as a migrant from a long-ago merger debris from a swallowed dwarf galaxy. Others whisper that the star has been riding the halo since the galaxy's earliest assembly. Kinematics don't give the age directly, but they point to the neighborhood where the star likely formed, and that narrows the story. So who are the headline fossils? There are bright, naked-eye subgiants whose carefully measured ages once brushed against the age of the cosmos, teaching us as much about our methods as about the star itself. There are iron-shy dwarfs whose spectra show iron weaker than any previous record, yet with carbon and magnesium painted clearly across the rainbow. There are Kafau-like stars that are extremely metal, poor without the usual carbon boost, suggesting different cooling channels in the gas that birthed them. Each is a different chapter in the same saga. The universe didn't need much metal to start making long-lived stars, but it needed just enough. All of this raises a deep question with practical stakes. How did gas cool quickly enough to fragment into small, long-lived stars when there were almost no heavy elements or dust? Carbon and oxygen can help by radiating energy away. Fine grains of dust from the first supernovae can help too, allowing the gas to clump. The fact that we see both carbon-rich and carbon-normal ancient stars suggests multiple pathways. The physics of the first clouds, their turbulence, their shock waves, their exposure to ultraviolet radiation likely decided which path each region took. Why should you care? Beyond the sheer wonder, because the chemistry we read in these time capsules sets the stage for everything that followed. Rocky planets need silicon, magnesium, and iron. Oceans and life need oxygen, carbon, nitrogen, and phosphorus. When we measure an ancient star's element ratios, we are measuring how quickly the universe loaded the pantry for future worlds. A star with almost no iron but plenty of carbon tells us that the pantry started with sugar before it got to pots and pans. In the next part of our journey, we'll slow down and read one record in full, line by line, element by element, what the spectrum of an ultra-metal, poor star actually says about a single, long-vanished supernova, and how that one explosion may have set the chemical thermostat for a whole region of space. Let's open the spectrum like a historian unrolling a scroll. A metal-poor star does not look dramatic in a photograph, but once you spread its light into a rainbow, you see a language of thin shadows. Each shadow sits at a precise wavelength, the street address of an element. First comes the scaffolding, hydrogen. The Balmer lines carve clean troughs in the blue. Their broad wings tell us the surface temperature broader means hotter, narrower means cooler. With temperature in hand, we estimate the surface pressure. Astronomers call it gravity by checking how some lines grow when particles crowd together. If they are wrong, every chemical abundance that follows bends out of true. Next is the fast metallicity check. Slide to 393 nanometers, where calcium leaves its deep K line. In a modern star, that line is bold. In a truly ancient one, it is ghostly. We measure how much light it steals its equivalent width, the width of a rectangle that would block the same area. Think of it as the line's strength in pixels. Weak calcium, given the star's temperature and brightness, points to vanishingly low metals overall. Now listen for iron, or rather, notice its silence. In sun-like stars, hundreds of iron lines pepper the visible rainbow. In our fossil, the iron forest thins into a few sparse trees. The gas that birthed this star had barely tasted supernova ash. To turn that headline into a number, we fit models of how atoms absorb light in the star's churning outer layers, accounting for motion, turbulence, and the sharing of energy between light and matter. From the few surviving iron lines, or from strict upper limits when none are seen, we derive FH, the iron to hydrogen ratio compared to the Sun. Then come the surprises. Even when iron is scarce, carbon can shout. Around 430 nanometers, a swarm of features from the CH molecule, the G band, leaps from the continuum like ink on vellum. If that band is strong, while iron is faint, we have a carbon-enhanced metal-poor star, the likely child of an early, lopsided supernova. Magnesium often joins the chorus near 517 nanometers with a triplet of lines. Elevated magnesium means the first exploding star forged plenty of alpha elements, the family assembled from helium nuclei in stellar furnaces. What about oxygen? In warmer stars, oxygen's cleanest optical lines are weak, so we estimate it indirectly using blended features or near-infrared transitions. Either way, carbon plus oxygen matters because those two are excellent coolants. Their presence in the birth cloud let the gas shed heat and fragment, so a small star could form and live for billions of years. Without those coolants, the first clouds would have favored only giants that died young. Lithium deserves its own paragraph. Fresh from the Big Bang, the universe made a trace of lithium along with hydrogen and helium. In old, warm, metal-poor dwarfs, lithium often sits at a nearly constant level, the famous plateau, a little lower than simple primordial predictions. If our target shows lithium near that level, its surface likely stayed quiet, and we are reading a clean fossil. If lithium is depleted, the star may have mixed it away during its life, or it may have formed from gas already altered by earlier stars. Heavy elements are the fingerprints of cataclysms. Europium, for example, is a neon sign for the rapid neutron capture process. If we see strong europium without the lighter S-process elements, the star is rich, and in rare cases we can attempt nuclear chronometry by measuring thorium and uranium. Those lines are weak and fussy, but when they can be measured, they whisper ages comparable to the universe itself. All of these measurements sit on a bed of careful housekeeping. We correct for the star's motion toward or away from us so the lines fall where physics says they should. We normalize the spectrum to a smooth continuum, the baseline brightness without lines, so the depth of each dip is measured against the right yardstick. We choose models that reflect the atmosphere, not a static slab, but a stew of rising and falling gas cells. In the most precise work, we account for departures from perfect equilibrium, sometimes called non-LTE, and even use three-dimensional simulations to reduce bias. Chemistry is only half the diary. Motion is the margin notes. With precise positions and velocities from astrometry, we compute an orbit. Does the star dive on a long, stretched loop through the halo? Does it carry the dynamical signature of a dwarf galaxy that merged with the Milky Way long ago? If its path matches a known stream, we can place its birth environment and compare its chemistry to siblings. When chemistry and orbit agree, confidence soars. There is one more trap to avoid: companionship. Some carbon-rich ancient stars got their carbon from a neighbor, a once giant companion that shed enriched material. To rule that out, we monitor the star over months and years to see whether its radial velocity wobbles. A steady speed argues for a single, self-made record. A wobble hints at past transfer. Either way, we learn something real about where the carbon came from and whether the star is a true time capsule. Pull back from the details and you see the plot. A faint calcium line, a hushed iron forest, loud carbon, and healthy magnesium. maybe a whisper of europium, maybe a trace of lithium. Together they sketch the profile of one of the first supernovae in that region, its mass, its violence, and how much of its heart fell back into a black hole. From that one death came the raw materials for a small, quiet star that has survived long enough for us to read it. The page is thin, the ink is faint, but the story is vivid once you know the alphabet of lines. In the next section, we will meet specific record holders, walk through what makes each extraordinary, and see how their chemical accents, carbon heavy, magnesium bold, rich, or nearly featureless, reveal different. Meet the record keepers, the handful of stars whose light reads like footnotes to the universe's first chapters. They look ordinary in small telescopes, but their spectra are loud with history. In each case, a pattern of thin lines reveals which elements were available when the star was born, what kind of explosion polluted its birth cloud, and sometimes even which small galaxy it came from. Line up these fossils and the first billion years unfold like a flipbook. Start with a celebrity hiding in plain sight. HD 140,280. The Methuselah star. It is a modest subgiant on a long halo orbit, bright enough for binoculars and poor in metals by solar standards. Early analyses placed its age tantalizingly close to the age of the universe. Later refinements pulled it back with healthier margins. The headline isn't the number, but the status. This nearby traveler is genuinely ancient, the sort of long-lived, metal, poor star that anchors our clocks and proves that the Milky Way's halo is a museum of survivors. Now swing the spotlight to the opposite extreme, where iron nearly vanishes. Sky Mapper's SMSS J313 6708 is a jaw-dropper. In high-resolution spectra, iron lines that usually pepper a star's rainbow are below detection, yet carbon and magnesium stand out clearly. Feed those clues into models of a first-generation supernova, and a picture emerges, mixing and fallback. A massive star exploded, but much of its iron-rich core fell back into the newborn black hole, while lighter outer layers escaped. Gas touched by that debris later condensed into a small, iron-starved, carbon-rich star that could live for billions of years. He 1327, 2326, and He 107, 5240 add new accents to that theme. Both are staggeringly iron-poor and strikingly carbon-enhanced, though their detailed patterns differ. One shows extra nitrogen and a hint of strontium. The other carries a different balance of alpha elements. These are not look-alikes, but variations on early, lopsided enrichment in tiny clouds. A little ash from one or two massive deaths was enough to set the chemical thermostat and let the gas fragment into long-lived stars. Their spectra do more than impress. They constrain the mass and explosion physics of vanished first-generation giants. Now meet the contrarian. SDSS Joan 102,915 plus 170. 2,927, often called Caffau's star. It is extremely metal-poor without the big carbon boost. For years, many models leaned on carbon and oxygen as must-have coolants for forming small, long-lived stars. This object points to an alternate path. Fine structure lines and dust grains can sometimes carry the cooling load even when carbon is not elevated. One star does not rewrite a theory, but it forces the theory to grow up and broaden the menu of early cooling channels. Some of the most revealing fossils live not in the halo, but in tiny satellite galaxies. Reticulum 2 is a famous example. It is an ultra-faint dwarf, so small you could sketch its bright members on a postcard, yet several of its stars glow with europium and other R-process elements. The cleanest reading is dramatic. A single neutron star merger early in that galaxy's life flooded the whole system with heavy nuclei. In one stroke, it showed that rare events can dominate small ecosystems, and that even the faintest galaxies can lock in a clear chemical signature. A different pair of benchmarks, He 1523, 901, and CS 31082. One lets us try nuclear chronometry. Their spectra include lines from thorium and, in one case, uranium. Those radioactive clocks tick slowly, but over billions of years they tick enough to measure. Compare the remaining amounts to stable neighbors, and you get ages that land near the age of the universe. The method is delicate and theory-dependent, yet the big picture is clear. Some of the galaxies are process-rich stars formed when the cosmos was still young, and they have been carrying that timestamp ever since. Chemistry is only half the identity card. Motion is the other half. Thanks to precise astrometry, we can tag some ancient stars to the debris of past galactic mergers. The Gaia-Enceladus event, nicknamed the Sausage, left a population on plunging, eccentric orbits with distinct chemistry. Find a metal-poor star with that kinematic signature, and you are likely holding a shard of a swallowed dwarf galaxy. Other moving groups, like the Helmy Stream, sketch different chapters of the Milky Way's assembly. Together, they turn the halo into a scrapbook of collisions. All these case studies point to a central lesson. The early universe did not paint the same chemical picture everywhere. In one region, a faint, fallback-prone supernova seeded gas with carbon and magnesium but little iron. In another, a dust-aided cloud cooled without a carbon boost and birthed a nearly featureless, iron-poor star. In a third, a rare but potent neutron star merger drenched a tiny galaxy with R-process elements in a single afternoon of cosmic time. The first billion years were not a smooth blend. They were a patchwork quilt stitched by different kinds of fire. One last character deserves a mention. The almost stars that never quite lit. Brown dwarfs born from ultra-primitive gas would be too dim to spot across the galaxy today. But if any exist nearby, they could carry the same chemical fingerprints without the distractions of a hydrogen-burning core. Finding them would be hard, yet the reward would be enormous. A fossil that never processed its own chemistry at all. Line up the cast, and a modest moral emerges. The universe did not need many first-generation explosions to set the table. A few asymmetric blasts, a few pockets of dust, and a single neutron star merger in the right place were enough to launch the cascade that led, in time, to spiral arms, habitable zones, and minds asking where it all began. In the next section, we will get practical. In a sky full of look-alike points, how do modern surveys find these needles? How do machine learning filters rank candidates? And how do giant telescopes spend precious nights chasing the rarest fossils without wasting a minute? Imagine you have 2 nights on a world-class telescope and 10,000 possible targets. How do you bet those hours on the right needles? Stellar archaeology uses a layered funnel. Wide surveys cast the net. Machine learning ranks the catch. Medium resolution, recon spectra verify the shortlist, and high-resolution observations read the chemistry line by line. Surveys come first. Photometric catalogs such as Pan-STARRS, SkyMapper, and Gaia provide colors, brightnesses, and motions for billions of stars. Colors hint at temperature, while parallax and proper motions separate nearby dwarfs from distant giants, so a faint, ancient dwarf is not confused with a brighter, younger giant. Some programs add surgical filters aimed directly at metallicity. The Pristine survey, for example, uses a narrow band centered on the Ka-H-K lines. If a star is relatively dim in that band compared to its broadband light, the calcium absorption is weak, and the overall metallicity is likely very low. Even at this early stage, extinction maps are used to correct for dust, so that a reddened modern star is not mistaken for a cool, metal-poor one. Then come low-resolution spectra at scale. Projects like SDSS, SEGU, JWST, and DESI feed thousands of fibers into a spectrograph and collect spectra for entire fields in a single exposure. At R20, you are not measuring uranium, you are asking quick, robust questions. Do the Balmer lines fit a sensible temperature and gravity? Is the CAK line faint for that temperature? Is there a CHG band hinting at carbon enhancement? Are we staring at an interloper like a quasar or hot subdwarf that mimics the colors but betrays itself in the spectrum? Automated pipelines answer these questions consistently and flag anything odd for a human to inspect. Ranking millions by eye would take lifetimes, so the next layer is algorithmic triage. Teams train models on stars with known labels. Random forests and gradient-boosted trees digest features like color indices, reduced proper motion, and quick line strength metrics. Convolutional neural networks go further by ingesting the entire low-resolution spectrum and learning the texture of metal-poor fingerprints. Semi-supervised and anomaly detection methods hunt the tails. Show me things unlike the bulk. Crucially, the models are tuned to be humble, better to pass a few false positives to recon than to discard a hyper-metal-poor gem. Before you spend a premium night, you sanity check with medium-resolution reconnaissance. Instruments with R5010 confirm weak calcium, measure the carbon G-band cleanly, and distinguish dwarfs from giants. This step also secures a precise radial velocity and starts the clock for binarity checks. If a target's velocity wobbles across months, past mass transfer from a companion may explain excess carbon, changing how you interpret the chemistry. Recon spectra are cheap compared to high-resolution time. They protect the schedule and sharpen the shortlist. High-resolution abundance work is the payoff. Keck, Hires, VLT, UVES, Subaru, HDS, and Magellan, Mike deliver R40-060. Zero spectra with enough signal-to-noise to detect faint iron lines and rare tracers like europium, thorium, or uranium. Exposure time calculators tell you whether a star needs 30 minutes or 3 hours. Dark time helps in the blue, where many key lines live. Steady seeing keeps the spectrograph efficiently fed. Stable conditions minimize drift. Observers plan a cadence. Bright standards at dusk and dawn to anchor the scale, telluric calibrators to remove atmospheric features, and repeated visits to suspected binaries. Reduction is unglamorous but decisive. Bias and dark frames are subtracted. Flats remove pixel quirks, and arc lamps set the wavelength solution. Echelle orders are traced and extracted. Cosmic rays are clipped. Blaze functions are corrected. Orders are merged, and the continuum is normalized. Cross-correlation with a template then yields the radial velocity, so every line lands at its laboratory wavelength. Only when the spectrum is stable and clean do you measure equivalent widths or fit synthetic spectra, line by line. Stellar parameters are the foundation. Effective temperature comes from Balmer line wings, or from dirdant colors calibrated against the infrared flux method. Surface gravity astronomers call it log G, is pinned by Gaia parallax plus isochrones, or by enforcing ionization balance between FEI and FE2 with non-LTE corrections where needed. Microturbulent velocity is tuned until abundances show no trend with line strength. With temperature, gravity, microturbulence, and overall metallicity set, you derive consistent abundances for carbon, oxygen, magnesium, silicon, calcium, titanium, and the neutron capture elements. Corrections matter most when metals nearly vanish. Interstellar absorption can add extra calcium in the blue, confusing simple photometric cuts. So teams compare nearby sightlines and check interstellar sodium lines to separate stellar from interstellar absorption. Non-LTE affects bias species like sodium, aluminum, and iron. In the hypermetal, poor regime, three-dimensional hydrodynamic atmospheres can shift key ratios by tenths of a dex. Best practice is to report the straightforward one-dimensional LTE results and the recommended corrections side by side so different surveys can be compared on common ground. Logistics can make or break a program. Multi-object facilities such as DZ, Weave, and Foremost place thousands of fibers per plate, but fiber collision rules and field geometry force compromises. Teams triage candidates, brightest and most extreme first, fainter outliers next, and a sprinkle of control stars each night to monitor systematics. Bright lunar phases are perfect for reconnaissance. The bluest high-resolution work earns the darkest hours. Afterward, open catalogs publish not only the labels, but also the selection functions, so theorists can apply the same biases when comparing models of early galaxy assembly to the data. Machine learning does not retire after the photons are captured. Data-driven labelers like the Canon and physics-informed emulators like the Pane learn the mapping from spectra to stellar parameters and abundances, then propagate uncertainties realistically. Active learning loops even ask for the one spectrum that would most improve the model if observed tonight, closing the feedback loop between survey, design, and discovery. Over time, this strategy gets sharper at finding the rare tails, hypermetal, poor dwarfs, carbon normal oddballs, and R-process beacons without flooding follow-up teams with noise. Put it together, and the funnel works. Millions of stars shrink to thousands of candidates, to hundreds confirmed metal, poor, to dozens so extreme that each can rewrite a paragraph of the first billion years story. Behind every headline fossil is an army of catalogs, filters, algorithms, plate design scripts, cloudy nights, and stubborn calibration. The magic is not that one star is special. It is that the system keeps finding them, steadily turning scattered relics into a coherent map of how the Milky Way assembled one thin spectral line at a time. Picture a single, ancient star suspended in the halo like a grain of ash caught in a sunbeam. It is dim, steady, and chemically almost blank, yet that blankness is exactly what makes it loud. Tonight we will translate its spectrum into a crime scene report about a vanished first star. Who exploded, how violently, what fell back into a newborn black hole, and how that one death set the thermostat for an entire cloud of gas. Start with the ratios that matter most. When magnesium and calcium are high relative to iron, the culprit forged lots of alpha elements and left little iron behind. That points to a mixing and fallback supernova. A massive star detonates. The outer layers, rich in carbon, oxygen, and magnesium, escape. Much of the iron-rich core falls back and vanishes. When the next star forms from that ash, it carries magnesium's signature and iron's absence like opposing fingerprints. If, instead, iron sits at a modest level and the alpha elements are only slightly elevated, you're looking at a more efficient explosion that ejected a healthier portion of the core. Carbon and nitrogen are the plot twists. Carbon tells you the outer layers were torn free. Nitrogen hints that the progenitor mixed material between its core and envelope before it died. Some hypermetal-poor stars show enormous carbon with modest nitrogen, as if the envelope was flung off before deep mixing. Others display both, implying a churning progenitor that stirred its interior like batter before the oven door blew open. Oxygen is cooling power. Elevated oxygen means the birth cloud could radiate heat effectively, letting it fragment into smaller clumps. That is how you get a low-mass survivor in a metal-poor environment. Carbon and oxygen give the gas a way to shed energy, and tiny pockets break off to form stars that can live for the age of the universe. Without them, the cloud would have favored only big, short-lived brutes great for fireworks, terrible for fossils. Sodium and aluminum trace the odd-even pattern, a subtle fingerprint from nuclear pathways in massive stars. If the even elements magnesium, silicon, calcium dominate and the odd ones lag, the progenitor probably died at low metallicity. The extreme version of this pattern, paired with lots of iron, is what theorists expect from pair instability supernovae, explosions of stars roughly 100 times the sun's mass that blow themselves completely apart. The catch? That unmistakable pattern is rare in the fossils we've found so far, which suggests such titanic deaths did not dominate the earliest chemical enrichment, or that their debris did not form many long-lived stars. Now tune your ear to the heavy end of the orchestra, where neutrons build exotic nuclei. Europium is the marquee for the rapid neutron capture, or R process. A star with iron scraping the floor but europium singing loudly is an R process beacon. It likely formed near a rare but potent event, most plausibly a neutron-star merger, or a special class of jet-driven supernova. Barium without europium points the other way, the slow neutron capture, or S process, which runs in aging giants. In truly ancient stars, strong S process can mean the carbon and barium came from a companion that puffed up and shared its enriched winds long after the star was born. That is why we watch for radial velocity wobbles. Chemistry without context can be a magic trick. Thorium and uranium, when detectable, turn the spectrum into a clock. Their steady decay lets you date the enrichment, the way archaeologists date a wooden beam. The uncertainties are real initial production ratios, and subtle modeling errors matter. But when thorium to europium or uranium to thorium ratios land near as old as the universe, you are looking at one of the galaxy's eldest citizens, and you can say so without crossing your fingers. All these ratios feed into yield models, numerical recipes that predict what different masses and explosion energies should eject. Imagine a menu: 15 solar masses, modest energy, little fallback; 25 solar masses, strong mixing and heavy fallback; 40 solar masses, jet-driven explosion with asymmetric ejection. For each menu item, the code simulates nuclear reactions and the hydrodynamics of the blast, then prints a table of expected elements. Your measured abundances are the waiter's ticket. Which kitchen order did nature deliver? The fit is never perfect, because real stars are messy and explosions are moody. That is where ensembles help. One fossil might suggest a 2030 solar mass progenitor with strong fallback. 5 fossils with similar patterns make the case stronger. A different group may cluster around milder explosions that made more iron. When you map hundreds of such fingerprints across the halo and the tiny satellite galaxies, a pattern emerges. The early universe was a mosaic of little kitchens cooking with different fires. Orbit ties the kitchen to the neighborhood. If our fossil rides an elongated path aligned with a known debris stream, it likely formed in a dwarf galaxy that later merged with the Milky Way. Compare its chemistry to siblings on the same stream. If they share the same odd magnesium to iron or barium to europium quirks, you've time-stamped an entire family. If they differ wildly, you're looking at a dwarf that churned through a few distinct enrichment episodes before it fell into the Milky Way's gravity well. Even the star's surface physics can sharpen the forensic sketch. Lithium near the old plateau suggests the surface has not been heavily stirred, preserving the original composition. Lithium far below the plateau can mean surface mixing erased the primordial trace, or that the gas was pre-processed by earlier stars that burned lithium away. Either way, lithium tells you how clean your sample is before you infer the crime. With one spectrum, you can already say a lot. The first enrichment here was lopsided. Iron fell back. Carbon and magnesium escaped. Oxygen helped the gas cool. The next generation fragmented. A small star formed and lived quietly for more than 13 billion years. With 10 spectra in the same moving group, you can say more. The group's parent dwarf saw one R process event early, then little else. Its star formation fizzled quickly. It was tidally shredded. Its children now lace the halo on long, plunging orbits. Scale up to hundreds, and you begin to test galaxy formation theories. Simulations must not only build a Milky Way of the right mass, they must also paint the correct metallicity distribution, the right fraction of carbon-enhanced stars, the observed spread in alpha elements at the lowest metallicities, and the timing of our process appearance. When a model overproduces iron at early times, your iron-poor fossils veto it. When it sprinkles our process too smoothly, your rich clumps in tiny dwarfs object. The fossils are not souvenirs, they are referees. Here is the wonder beneath the numbers. A star with almost no iron, a pinch of magnesium, a generous scoop of carbon, and a whisper of europium is not just a point on a plot. It is a letter from a single, short-lived giant that died before galaxies had settled into disks. That giant never knew planets or people. It never saw a spiral arm or a comet's tail, but it taught the gas how to cool. It salted the universe with the first ingredients for rocks and oceans. It made possible every quiet, sun-like star that came after. When you read a fossil spectrum, you are not decoding a relic. You are watching the moment the universe learned to build. Think bigger than a single fossil. Imagine draping a chemical map over the Milky Way, every point of light tagged with a tiny barcode of elements and an arrow showing its motion. That is galactic archaeology today. Chemistry plus kinematics read together, turning a fog of stars into a family tree. The halo becomes a collage of immigration stories. The thick disk looks like a city built in layers. Start with a simple census. How many stars sit at each metallicity? The halo's metallicity distribution peaks around a few thousandths of the sun's iron and then thins into a rare tail where hypermetal-poor stars live. Even the peak teaches something. The early galaxy enriched quickly. A handful of vigorous bursts of star formation and supernovae dragged the average metallicity upward long before the thin disk settled into its quiet spiral routine. Another pattern jumps out when you sort by chemistry. At low metallicity, there are two main tracks. One group shows high alpha elements, magnesium, silicon, calcium, relative to iron. The other is alpha-low, high alpha stars likely formed in crowded, intense environments, where core collapse supernovae dominated the chemical budget. Alpha-low stars look like immigrants from smaller galaxies where the clock ran slower. Type Ia supernovae had time to add iron and dilute the alpha signal. When Gaia reveals that alpha-low stars ride eccentric radial orbits, the merger story snaps into focus. The largest of those arrivals wears a tabloid nickname, the Sausage, or Gaia-Enceladus. Its debris dominates the inner halo, with stars on radial paths that dive through the galaxy like stones skipping across a pond. A different family, the Helmi stream, threads a narrower lane with its own kinematic fingerprint. Each stream is a chapter. Together, they turn the halo into a scrapbook of collisions. Zoom out, and the halo itself looks dual. An inner component, thick with Enceladus debris, and a more tenuous outer halo with colder, often retrograde orbits. The outer reaches carry more extreme metal-poor fossils, likely born in tiny proto-galaxies far from the main action. Find an ultra-metal-poor star on a wide, backward path, and you are probably holding a shard from the galaxy's hinterlands. Now turn to the disk. Metal-poor does not mean only halo. Some ancient stars live on prograde orbits in the thick disk with chemistry that shouts, formed early, in situ. Their alpha ratios are high and their ages grand. They are the basement stones under the Milky Way's modern floors. Comparing them to alpha-low halo immigrants lets us separate what the galaxy built for itself from what it swallowed later. All this rests on a physical hinge called the critical metallicity, the threshold at which gas can cool and fragment into small, long-lived stars. Two mechanisms compete. One uses fine structure line cooling from carbon and oxygen atoms. The other uses dust grains forged in the first supernovae. Both pathways likely operated, sometimes together. That is why we find both carbon-enhanced fossils and rare carbon-normal, iron-poor outliers. The threshold is not one magic number, but a neighborhood set by density, turbulence, and radiation. The point where cooling finally outpaces gravity's heating, so the cloud can break into small pieces. Reionization weaves through this, too. As the first galaxies lit up, their ultraviolet light ionized the intergalactic medium. That background choked off gas supply to the tiniest halos and heated their outskirts. If you catch an ultra-faint dwarf whose stars are all ancient, you may be seeing a system that formed quickly and then had its fuel cut by the rising ultraviolet sea. Its chemical record freezes at an early time, a few alpha element bursts, maybe a single R process splash, then silence. Chemical tagging aims to go further than stream or dwarf. In principle, stars born in the same cloud share a multi-element fingerprint. Measure a dozen elements with high precision, and you get a point in a high-dimensional space, your barcode. Cluster analysis in that space can regroup siblings long after gravity has scattered them. But the winds are mounting. Dissolved clusters reassemble in abundant space even when their orbits have blurred. And some moving groups split cleanly into multiple birth families once chemistry is considered alongside motion. There is also the human factor. Time on telescopes is precious, and algorithms have biases. That is why open catalogs, shared selection functions, and reproducible pipelines matter. When teams publish not just which stars they found, but how they found them, theorists can apply the same filters to simulations. Apples compare to apples. A model of early assembly must pass more than a looks-right test. It must reproduce the observed fraction of carbon-enhanced stars at each metallicity, the scatter and alpha elements at the lowest metallicities, and the timing and clumpiness of our process enrichment. Bring the pieces together and a narrative emerges. A few 100 million years after the Big Bang, tiny halos formed the first giants. Their deaths salted nearby gas with carbon, oxygen, and magnesium. Some iron fell back. Dust grains floated out of the ashes. In that cooled, speckled medium, the first long-lived dwarfs formed our fossils. Larger halos merged. Some dwarfs were digested. Streams stretched across the sky. The Milky Way's inner halo took shape with a dominant immigrant, Enceladus. The thick disk rose as gas settled and formed stars quickly, stamping them with high alpha ratios. Later, the thin disk unfurled, and ongoing chemistry smoothed the palette, but the oldest barcodes remained legible for anyone with a spectrograph and patience. Here is the payoff for listeners. When you hear metal, poor, don't translate boring, translate earliest chapters. Each of these stars is a receipt for a specific kind of fire, a specific kind of merger, a specific moment when cold gas learned to make something enduring. They are the quiet witnesses that let us say, with a straight face, how our galaxy grew from sparks into spirals, and how the ingredients for worlds like ours arrived on time. Think of two flashlights pointed at the same dawn. One looks across the universe to the first galaxies. The other looks nearby at the oldest stars in our halo. When those beams overlap, guessing turns into cross-checking. That is the power of pairing high redshift astronomy with stellar fossils. Two views of the same beginning that can confirm and correct one another. The far look belongs to infrared observatories that detect baby galaxies a few 100 million years after the Big Bang. Expansion shifts their starlight into longer wavelengths, so the most telling features live in the infrared. From those galaxies, we learn the big strokes. How quickly stars switched on, how much ultraviolet light escaped to reionize the cosmos, and how fast heavy elements appeared in bulk. The near look comes from high-resolution spectra of metal-poor stars that lock in the chemistry of those early events. Here is the dialogue in practice. If distant galaxies already show oxygen and carbon, then fossils born shortly afterward should carry those same coolants. If young galaxies look dust-rich, dust must have condensed quickly in first supernovae, something we can test locally, because dust-aided cooling offers a path to forming carbon normal, iron-poor stars without an extreme carbon boost. Quasars add a third vantage: gas clouds between us and a bright quasar imprint. Absorption lines, a barcode without starlight. Some damped Lyman alpha systems at high redshift are astonishingly metal-poor. Compare their carbon to iron or silicon to iron ratios to those in halo fossils, and we learn whether the same kinds of supernovae seeded both environments or whether mixing, outflows, and time stretch the story differently. Gamma-ray bursts provide a flashbulb. When a massive star dies and jets punch out, the fading afterglow lights gas in and around the host. For a few hours, we can read element ratios in star-forming regions less than 1 billion years old. When those ratios rhyme with local fossils, alpha elements high, iron low, the case strengthens that ordinary core collapse supernovae dominated early enrichment. Another global channel is the 21-centimeter whisper from neutral hydrogen. Before and during reionization, that line records how the first stars and black holes heated and ionized the cosmic web. Models that fit the timing must pick star formation histories and feedback strengths. Fossils police those choices. Too many very massive stars imply pair. Instability yields our fossils rarely show. Too few early explosions fail to make the observed carbon-enhanced fraction. Uncertainty also lives on Earth. The R process clock needs nuclear reaction rates that set how thorium and uranium were produced relative to europium. Laboratory work tightens those numbers, shrinking age errors. Better opacities and atomic transition probabilities sharpen abundance measurements, too. Every update in a data table can move a point on the cosmic timeline. The stellar atmosphere is the last filter. Real photospheres are three-dimensional, granular, and not always in thermodynamic equilibrium. For metal-poor stars, accounting for those effects can shift key ratios by tenths of a dex, the difference between iron undetected and iron extremely low. Best practice now is to report simple, one-dimensional LTE results alongside recommended 3D, non-LTE corrections. The next leap is imminent. Giant ground-based telescopes, ELT, TMT, and GMT, will feed ultra-stable spectrographs aimed at the blue and near UV, where many key lines live, pushing precision work to fainter stars and smaller dwarfs. Multi-object instruments like WEAVE, Foremost, and Subaru's PFS will deliver reconnaissance spectra by the hundreds of thousands. Future UV missions will access clean lines above the atmosphere and lock down oxygen and iron peak diagnostics. As the data flood grows, the strategy shifts from chasing record holders to mapping distributions. We will compare abundance spreads across the inner and outer halo, known streams, and dozens of ultra-faint dwarfs. Are there metallicity floors that mark reionization's cutoff? Two-shot R-process histories in some dwarfs? Do accreted systems carry a different carbon-enhanced fraction than in-situ populations? Simulations are ready for grading. Modern zoom-ins track individual elements, allow asymmetric mixing and fallback, grow and destroy dust, and follow bound clusters that later dissolve into the halo. We can pull a mock stream and ask for its carbon-to-iron distribution. If it disagrees with the sky, we tune feedback, the initial mass function, or merger timing until it sings the same tune. Beneath all this, engineering beats a simple pulse. We are using dead stars to learn how to live. The first heavy elements made rocks and rain and chemistry that climbs toward biology. A spectrum with almost no iron but generous carbon is a permission slip for future worlds. A tiny dwarf blazing with europium is a signature of the universe learning to make the stuff of continents and compasses. Next, we leave the overview for a small stage, a single ultra-faint dwarf galaxy, star by star, to see how one R process bonfire and a handful of early supernovae carved a chemical landscape you could sketch by hand. Picture a galaxy in miniature, a loose handful of ancient stars hanging under the Milky Way's bright disk. We will read that diary one ultra-faint dwarf galaxy, member by member, and watch how a few early explosions set the chemistry for everything that followed. First, the map. The system is tiny, with a shallow gravitational well and a low escape speed. Its total light mimics a star cluster, but its stars span a genuine metallicity range. Some sit near an iron to hydrogen ratio of -2, others plunge below -3. That spread is the signature of a galaxy. Clusters form in a single burst and stay chemically tight. Dwarfs assemble in small, messy steps. Membership matters. Astronomers use wide-field imaging plus precise proper motions and radio velocities to find stars that move together. Bright red giants become the first targets because their lines are strong. Later, deeper exposures add fainter main sequence members. Several giants show heavy element lines, especially europium and barium, far stronger than their iron suggests. That pattern points to the rapid neutron capture process, the R process. It makes europium in environments flooded with neutrons. In large galaxies, its products smear out across space and time. In a system this small, a single event can dominate the neighborhood. The most natural reading is that an early R process source, most likely a neutron star merger, perhaps a jet-driven supernova, went off while the gas reservoir was still small and poorly mixed. The ejecta drifted through the dwarf and seeded some clouds more richly than others before they collapsed into stars. Timing sharpens the picture. Ultra-faint dwarfs have short star formation histories. Many appear to shut down within a few 100 million years, choked by the rising ultraviolet background of reionization and by their own supernovae clearing gas. If an R process event saturated the chemistry that early, its delay must have been brief. Look across the rest of the periodic table and more texture appears. Magnesium, silicon, calcium, and titanium sit high relative to iron, the classic imprint of core collapse supernovae. Carbon varies from star to star. A few members are carbon-enhanced, likely tracing lopsided early explosions or, in some cases, mass transfer from a long-gone companion. Most are not. Not every member is rich. A handful with iron below -3 show almost no heavy element features at all. Those are the unpolluted floor, formed before the bonfire smoke had spread. Their alpha elements are high, their iron peak elements are low. Their carbon ranges from ordinary to elevated. Together, they outline the pre-bonfire weather. Ordinary core collapse yields dropped into pockets of gas where mixing was inefficient and each event mattered outsized. Motion ties chemistry to origin. Proper motions from modern astrometry trace a long, looping orbit that brushes the Milky Way's outer halo. Tides shave stars from the dwarf's flanks, peeling thin streams like threads. Some rich members already ride those threads, which means the R process signature is not confined to the surviving core. It is seeding the halo with tagged tracers. Find a halo star on the same stream with the same heavy element barcode, and you have matched a child to its parent. Small samples make the story feel personal. Imagine 10 bright members with high-resolution spectra. 6 show europium, towering over iron. 4 do not. The rich group cluster around europium to iron values that would be shocking in the field halo. Yet here they look normal because the whole system bathed in the same ash. The iron spread reaches a full dex, proof of multiple bursts and poor mixing. Puzzles remain, and they are fruitful. How did the dwarf keep gas long enough after the R process blast to form enriched stars when escape speed is so low? Perhaps the event occurred off-center. So much of the ejecta drifted rather than rammed dense gas. Perhaps the timing landed between earlier core collapse supernovae, when the medium had cooled and clumped again. Or perhaps the R process engine was less kinetic than feared, delivering chemistry without catastrophic mechanical damage. Each option can be tested as more dwarfs are mapped in detail. Even the housekeeping is instructive. Interstellar absorption can fake extra calcium in the blue, so teams cross-check with sodium lines to separate stellar from interstellar signals. Non-LTE affects bias, light elements at the lowest metallicities, so best practice is to publish straightforward one-dimensional results alongside recommended corrections. Repeated velocity measurements weed out binaries whose late-life mass transfer could masquerade as a primordial carbon boost. Now pull back to meaning. This one postcard galaxy says that heavy elements arrive in lumpy packages. A single rare event can define a whole ecosystem's chemical identity. Early chemical evolution was not gentle diffusion, but stepwise jumps with long, quiet stretches between. And there is a gift to galactic archaeology, a portable tag. When the Milky Way tears a dwarf apart, its children disperse. But their R-process accent travels with them. Across the halo, we can still hear the echo of that single fire. The moral is humble and grand at once. You do not need a billion stars to learn first principles. You need a handful measured well, a sense of the clock they carry, and the patience to compare them honestly to models. In a system this small, nature ran a clean experiment. One R-process spark. A few ordinary supernovae. Limited time, shallow gravity. From that, a chemical landscape you can keep in your head and sketch by hand. In those lines lies a story about how the universe moved beyond hydrogen and helium to rocks, oceans, and mines. Next, we leave the miniature for a puzzle closer to home. Could the sun itself have been born in a chemically exotic nursery? And do any solar siblings still carry subtle barcodes that lead back to our birth cloud? Imagine rewinding the Milky Way to the afternoon our sun was born. The nursery was probably not a quiet cul-de-sac, but a crowded, high-mass star-forming complex. Meteorites say so. The oldest inclusions carry fingerprints of short-lived radioisotopes, especially aluminum-26 and iron-60, whose half-lives are only a few million years. Those nuclides must have been forged by nearby massive stars, delivered by a Wolf-Rayet wind or a close supernova, then mixed into the proto-solar disk on a deadline. Something energetic lit the match, and it happened in our neighborhood. If the sun formed in a rich cluster, it had siblings. Hundreds to a few thousand stars born from the same well-stirred cloud. Open clusters today show how uniform such families are. Their members match in detailed abundances to exquisite precision. Clusters, however, are fragile. Tides, spiral arms, and close flybys peel them apart within a few 100 million years. After 4.6 billion years, the sun's siblings should be smeared around the disk like confetti, some ahead of us, some behind, many far above or below the plane. Can we still find them? The search has 3 filters: chemistry, motion, and age. Chemistry comes first. Chemical tagging treats a star's multi-element pattern as a birth certificate. Dozens of ratios: carbon, oxygen, magnesium, silicon, nickel, yttrium, barium, and more encode which massive stars seeded the cloud and how fully the gas mixed. 2 unrelated stars can share the same overall metallicity and still disagree in the fine print. 2 true siblings should agree line for line within tiny tolerances. The sun complicates its own case. Compared to many solar twins, it looks slightly deficient in refractory, rock-loving elements relative to volatiles. One plausible cause is planet formation. Locking refractories into planets and planetesimals left the solar photosphere a hair leaner in rock. If that reading is right, the quirk is either a helpful flag, some siblings might share the same depletion, or a hazard that makes the sun look chemically odd even among kin. Either way, it is a feature to test, not to ignore. Motion is the second sieve. With Gaia's precise positions and velocities, we integrate orbits backward in a realistic galactic potential to ask which stars could have shared the sun's neighborhood 4.6 billion years ago. The problem is chaos. Spiral arms, giant molecular clouds, and the Milky Way's bar kick stars around, blurring orbits over gigayears. Radial migration likely moved the sun thousands of light years from its birth radius. So dynamics alone cannot prove kinship. They can only say plausible or no way. Age is the third check. Siblings must be coeval with the Sun within a few percent. That is tough. For Sun-like stars, gyrochronology and isochrones carry wide error bars. Astroseismology reading starquakes can do better, but only for bright targets. In practice, teams filter candidates by chemistry and motion, then keep only those with ages consistent with 4.6 billion years. The survivors get premium spectra to confirm the barcode pixel by pixel. Have we found any? A few nearby stars have passed 2 of the 3 tests, and 1 or 2 remain intriguing on all 3, but no consensus golden sibling exists. A romantic candidate, the open cluster M67, shares the Sun's age and composition, but is an unlikely birthplace once dynamics are traced back. The honest headline is that siblings are hard. Billions of stars to sift, subtle barcodes, blurry orbits, and fussy ages. Hard is not hopeless, just slow. Meteorites keep whispering about the nursery. Calcium-aluminum-rich inclusions record early heating. Iron-60 demands supernova ejecta mixed into the disk within a few million years. The shapes of the Kuiper belt and the detached orbit of Sedna hint that a passing star brushed the young solar system while it still lived in a cluster, lifting distant perihelia and helping seed the Oort cloud. Even today's layout carries scars of a crowded childhood. What does an exotic nursery mean for habitability? A nearby massive star can photo-evaporate disks, choking off planet formation, yet our system kept enough gas to grow giants and enough dust to build rocks. That argues for a Goldilocks placement, close enough to harvest radionuclides. Extra aluminum 26 may have warmed planetesimals from within, yet far enough to avoid having the disk stripped bare. Radiogenic heat could have helped early bodies differentiate and retain water, a quiet assist to future oceans. The roadmap from here is clear. Multi-object spectrographs will measure dozens of elements to parts per thousand precision in millions of stars. Machine learning tools will cluster that chemistry in high-dimensional space, while Gaia continues to map phase space streams left by radial migration. Cross those 2 atlases and likely families pop out. Then astroseismology and precision ages will winnow the roster. The endgame is not 1 star with a ribbon. It is a short list, perhaps tens whose chemistry, motion, and age agree. What do we gain if we confirm a sibling? Calibration. A Sun-mass sibling with a Jupiter analog tests how typical our architecture is given the same starting mix. A sibling without refractory depletion would challenge the planet fingerprint idea. A young Sun-like star in a dissolving cluster shows, in real time, how winds and ultraviolet light sculpt disks like ours. Each sibling is a control experiment nature ran for us and then scattered helpfully across the sky. There is a poetic payoff, too. Point a telescope at a nondescript G-type star a few hundred light-years away and say, with evidence, you and we were born in the same cloud, dusted by the same dying giant. The night feels smaller, our address more specific. Former resident of a lost cluster, sibling to stars X, Y, and Z. The Sun stops being an only child. It becomes a member of a family we are finally learning to recognize. Next, we return to the fossils themselves and pull on a different thread. Why carbon-enhanced? Iron-poor stars may have been the midwives of long-lived dwarfs, and what their frequency says about the first supernovae and the cooling channels that built the earliest small stars. Carbon-enhanced, iron-poor stars look like blank pages until you learn to read them. In a near-pristine cloud, gravity tries to compress the gas while pressure resists. Nothing fragments until the gas can shed heat quickly. A trace of carbon or oxygen can do it, radiating in fine structure lines and letting pockets of gas break into subsolar clumps. In that sense, carbon is not just an element, it is a midwife. Astronomers file these fossils under one label, CEMP, carbon-enhanced metal. Poor, but the family splits into branches. SEMP stars carry strong barium and other S-process elements, usually donated by a former giant companion. SEMP-R and SEMP-R S show heavier R-process accents. The most revealing branch is CMP. No, abundant carbon but little or no neutron capture enrichment. Those are most likely to record a first supernova's chemistry without later edits. Cooling sets the stage, and there are two main routes. Line cooling uses the C2 and OI fine structure transitions, which radiate efficiently at low density. Dust cooling uses tiny grains condensed in supernova ejecta. Collisions with gas share energy and the grains glow thermally. Either path can push gas past a threshold where it fragments into many small pieces instead of one massive star. Observers test the line cooling route with a compact diagnostic, often called a transition discriminant, that blends carbon and oxygen into one measure of cooling strength. Most of the most iron-poor survivors land on the cooled side, and many are carbon-rich. The lesson is double. A little carbon goes a long way, and early enrichment was patchy across space. SEMP-No stars trace the carbonated channel vividly. Their patterns fit mixing and fallback supernovae. Much of the iron-rich core fell back into a newborn black hole, while carbon-bearing outer layers escaped. Gas seeded by that debris cooled rapidly and fragmented into long-lived dwarfs. In ultra-faint dwarf galaxies where mixing is weak and each event matters, SEMP-No stars are especially common among the most iron-poor members. But the cosmos allowed a second path. A handful of extreme carbon-normal stars at ultra-low iron Cathau-like objects show that dust alone sometimes did the job. Supernovae forged grains. Reverse shocks destroyed some, not all. Surviving silicates, amorphous carbon, and tiny oxides seeded new clouds. Where grain abundance and density aligned, dust cooling by itself let gas fragment into small stars. Critical metallicity is therefore a neighborhood set by conditions, not a single magic number. Detectability shapes the census. Carbon announces itself through the CHG band near 430 nanometers, which can stand tall even when iron is nearly invisible. That makes SEMP stars easier to flag than carbon-normal fossils at the same iron level. The gift hides a trap. Surveys that lean on the G-band naturally harvest more carbon-rich objects. Modern teams model this bias explicitly to estimate how many carbon-normal ghosts they are missing. Binarity adds another wrinkle. SEMP stars frequently show radial velocity wobbles, the signature of a past donor that transferred carbon-rich material. SEMP-No stars wobble less often, strengthening the case that their chemistry is primordial. Long monitoring is still crucial. Without it, some mass transfer cases can masquerade as pristine fossils and muddy the cooling story. Plot the SEMP fraction against metallicity, and the trend is clear. Toward lower pH, the fraction climbs, yet the curve is not universal. The inner halo, debris from ancient mergers, and ultra-faint dwarfs each draw different slopes and scatters. Those differences encode the pace of star formation, the arrival of iron from type Ia supernovae, the survival of dust, and the strength of outflows. Element ratios sharpen the diagnosis. Many SEMP-No stars show high magnesium with ordinary silicon fits to mixing and fallback models rather than the distinctive yields of pair instability giants. Nitrogen varies, hinting at how much internal stirring the progenitor endured before it died. Lithium, when measured, often sits below the classic plateau, signaling surface mixing or pre-processing in earlier stars. Why does the balance of SEMP and carbon-normal fossils matter? Because it is a lever on the first stellar mass function. If low-mass survivors required either carbon or dust, then the timing and geography of those coolants dictated how many dwarfs each burst produced. Too few coolants and the early universe skews top-heavy lots of fireworks. No long-lived witnesses. Enough coolants in enough pockets and you get what we see. Many carbon-enhanced stars at the lowest iron, plus a stubborn carbon, normal minority that points to dust-led cooling. There is a practical payoff. SEMP signatures act like lanterns in survey data, pulling the eye and the algorithms toward the most primitive candidates quickly and saving precious high-resolution time for the likeliest fossils. As long as we keep the biases in view and chase carbon-normal candidates with equal care, those lanterns light the map rather than distort it. Step back, and the metaphor comes full circle. The first heavy elements were not decorations, they were tools. Carbon and oxygen were radiators. Dust was insulation and coolant. With them, gravity sculpted fine detail, carving small, patient stars from hot, stubborn clouds. Those stars are still here, whispering that a few atoms, in the right place at the right time, changed the fate of the universe from a brief blaze of giants to a cosmos with memory. Next, we visit the factories that supplied those tools. The first dust forges. How much dust did early supernovae really make? How much survived their own shockwaves? And how did that gritty inventory shape the birth of the earliest long-lived stars and, much later, the first rocky worlds? Dust is not a nuisance in astronomy. It is a technology. Smoke. Sized grains turn hot gas into a medium that can cool, clump, and spawn small stars. And, later, rocky worlds. The first factories were violent forges, massive stars dying as supernovae, and, perhaps, fast carbon, rich winds from Wolf-Rayet stars. In the near-primordial universe, there were no elderly red giants to shed dust at leisure. If dust appeared early, supernovae had to make it. Picture a fresh supernova a few hundred days after the blast. The ejecta expand and cool, temperatures fall below a few thousand Kelvin, atoms find partners and condense. Chemistry is local and picky. Where carbon outnumbers oxygen, carbon wins, building amorphous carbon grains. Where oxygen dominates, silicates and oxides nucleate tiny seeds of olivine, pyroxene, and alumina. The first condensates are nanometers across, a soot-fine fog forming in a storm. We have watched this chemistry unfold. In the mid-infrared, warm dust glows as it absorbs and re-emits the fading light. At sub-millimeter wavelengths, cold reservoirs appear that optical telescopes miss. Molecules like CO and CO flare up as intermediates, stepping stones toward grains. Famous remnants show both warmth and cold, newborn dust close to the center, and larger, colder masses farther out. The headline is simple. Supernovae can make a lot of dust quickly, but a destroyer waits at the door. As the debris plows into circumstellar and interstellar gas, a reverse shock drives back into the ejecta at thousands of kilometers per second. That shock heats and sputters grains, knocking atoms off their surfaces and sometimes shattering them. Survival is a size contest. Large grains, a tenth of a micron and up, endure. Tiny grains erode. Clumping helps, too. Dense knots can shield grains from the harshest passage and let more survive to adulthood in the interstellar medium. This balance, condense early, then survive. The reverse shock decides whether supernovae are net dust producers or dust myths. Observations show both sides. Some remnants carry large masses of cold dust, decades to centuries after the blast, implying efficient condensation and partial survival. Others show clear signs of destruction where the reverse shock has swept through. The picture is nuanced. Early supernovae likely seeded the universe with substantial dust, but the yield depended on grain size, clumpiness, and local shielding. Why does this matter for our fossils? Because dust is a cooling machine. A single grain colliding with hot gas shares energy and then radiates infrared light. In low metallicity clouds, where atoms alone struggle to shed heat, dust takes over at higher densities and helps the gas fragment into many small clumps. That is the dust-led path to low-mass, long-lived stars, the sibling of the carbon and oxygen line cooling path we met earlier. Where both channels were present, fragmentation became easier still. There is a planetary dividend. The solids that build planets are dust grains made sticky. In disks around young stars, grains collide, stick, grow into pebbles, then boulders, then planetesimals. The earlier the cosmos had dust, the earlier it could, in principle, assemble rocky worlds. Observations of galaxies less than 1 billion years after the Big Bang already show heavy dust burdens. That does not mean continents at cosmic dawn, but it does say the raw materials for rock were stockpiled early. Fossils point back to the forges. Some of the most iron-poor, carbon-normal stars imply that dust cooling alone enabled their birth. Their clouds likely contained silicate and oxide grains forged in early supernovae, even without a big carbon surplus. That reading strengthens when those stars live in ultra-faint dwarfs, where one dust-rich event can dominate the inventory. The mirror case extreme carbon enhancement with little iron argues that fine structure line cooling sometimes carried the load with minimal dust. Both channels likely operated side by side, their relative weights set by local chemistry and timing. Simulations knit these pieces together. Start with a small protogalaxy seeded with a handful of massive stars with different masses, spins, and explosion energies. Let some blasts be strong and clean, others messy with fallback into newborn black holes. Follow the chemistry that condenses grains. Follow the shocks that erode them. Allow clumps and shadowed pockets to protect a fraction. Then let the gas cool with both lines and dust, fragment, and form new stars. The goal is simple but strict. Reproduce the observed mix of fossils. New instruments are tightening the screws. Sensitive mid-infrared eyes watch fresh dust condense and then track how much survives as the reverse shock sweeps back. Sub-millimeter arrays trace cold grains long after the spectacle fades. Space-based infrared observatories peer into galaxies at cosmic dawn and weigh their dust when the universe was still a toddler. Each measurement narrows the wiggle room in our cooling story. If there is a single lesson from the dust forges, it is that the early universe did not wait for gentler times to make complexity. It built radiators in the midst of violence. Shattered stars gave future clouds the ability to shed heat and break into fine structure. Those grains later became the powder for worlds. When you hold a stone, you are holding the cooled breath of ancient fire. Next, we pull the camera back to the element makers themselves, the first massive stars, and ask what their masses, spins, and magnetic fields were like. How often they died quietly into black holes versus exploding, and how that balance sculpted the chemistry our fossils still carry. Call them the universe's first metalworkers. The very first massive stars, population 3, lit up in pockets of pristine hydrogen and helium and ran the nuclear forges that created the first carbon, oxygen, and magnesium. They burned hot, burned fast, and died young, leaving almost no direct fossils. What we know about them comes from their chemical ghosts imprinted on later stars and from simulations that follow gravity and gas as they dance in the infant universe. Start with mass, because mass is destiny. Early ideas favored lone giants of several hundred suns. Gas cooled only by molecular hydrogen does not collapse into a single colossus. It fragments into a small, turbulent crowd. The first stellar nurseries likely produced a top-heavy, spread many stars of a few tens of solar masses, plus some heavier outliers. That mix matters because it sets the yield table. 20 to 60 solar mass stars create plenty of alpha elements and only modest iron if the explosion is faint, or if iron-rich cores fall back into newborn black holes. A minority of more energetic blasts throw more iron and trace elements like zinc and cobalt into space. Rotation is the secret spice, with almost no metals to drive strong winds. First stars probably kept much of their spin. Fast rotation stirs the interior, dredging carbon and nitrogen from the core and spreading them toward the surface. In the most extreme cases, stars evolve almost homogeneously well mixed from center to edge, which changes which layers explode and which peel away. Rotational mixing can boost nitrogen even when iron is scarce. a pattern that appears in some ultra-metal-poor fossils. High spin can also set up jet-driven explosions when the core collapses. Magnetic fields are the rails those jets run on. Even faint seed fields amplify during collapse. If rotation is high, a magneto-rotational engine can launch narrow, relativistic outflows that carry freshly made elements. That does not mean every early supernova minted the rarest elements, but it offers a natural channel to explain the occasional rich star in a tiny galaxy before neutron-star mergers became common. Binarity complicates the plot in a good way. Fragmenting clouds make binaries and triples. Close pairs exchange mass, merge, and spin one another up. A mass-gaining star can look chemically young and rotate rapidly. Binary interaction can also strip envelopes and set the stage for collapsers' fast-spinning cores that power long gamma-ray bursts. The first generation was not just massive, it was social, and social stars leave different chemical wills than loners. Now the fates. For masses around 1040 suns, neutrino-driven core collapse supernovae are the baseline. They make strong alpha elements and a moderate dose of iron. Push the mass or the explosion energy higher, and you get hypernovae, more zinc and cobalt, broader mixing, and larger iron yields. With high rotation and magnetic fields, you may get a jet-driven event with asymmetric yields. Dial the mass higher still, and some stars never explode. Their cores fall straight into black holes, swallowing most of the iron they forged. That faint supernova channel matches fossils that show abundant carbon and magnesium but almost no iron. Then come the celebrities that rarely appear: pair, instability supernovae. In roughly 140-260 solar mass stars, high-energy photons turn into electron-positron pairs, softening pressure and triggering a runaway that unbinds the whole star. The yields are spectacular, lots of iron and a distinctive odd, even pattern across the periodic table. Such signatures are scarce in metal-poor fossils. That does not erase the events, but it says they were not the main chefs seasoning the early Milky Way. Environment decides how far those yields travel. In tiny halos, the escape speed is low. A few hypernovae can loft gas out and pause further star formation. Ultraviolet radiation from the first O-type stars ionized and heated their neighborhoods, carving bubbles and shredding molecular hydrogen. That Lyman-Werner background could suppress cooling in the smallest halos and delay the next round of stars. The first massive stars did not just make elements, they edited the stage on which the next actors performed. Winds matter too. At zero metallicity, line-driven winds are weak, yet rotation and surface enrichment can still peel off layers late in life. Those gentle leaks carry CNO elements into the medium even if the final core collapses quietly. The pattern elevated carbon or nitrogen with minimal iron resembles some carbon-enhanced iron-poor stars. Think of it as a two-step, slow seasoning by wind, then a faint or failed explosion that adds little iron. Put the pieces together and you get a menu of progenitors. Modest mass with ordinary core, collapse. Higher mass with energetic hypernova. Fast, spinning, magnetized cores launching jets. Quiet collapses that lock iron away. And the rare pair, instability fireworks. The halo's Atlas high alpha at low iron, frequent carbon enhancement, rare, odd, even signatures, and occasional ridge spikes argues that mixing and fallback explosions dominated, with a minority of hypernovae and jet events. The balance matters beyond chemistry. Quiet collapses and collapsers seed black holes quickly. Stack a few early mergers and you are on your way to the massive black holes that powered bright quasars within the first billion years. The same physics that left some fossils nearly iron-free may also explain the rapid growth of early giant black holes. What will sharpen this portrait? Better fossils and better models. More hypermetal-poor stars with precise zinc, cobalt, and nitrogen will pin down the hypernova and rotation footprints. More R-process maps in ultra-faint dwarfs will test jet channels. Simulations that follow magnetic fields, rotation, dust, and radiation together will show which mix of fates reproduces the sky's barcode statistics. Here is the headline to carry forward. The first massive stars were not caricatures. They were a mixed neighborhood of fast and slow spinners, singles and binaries, modest and monstrous masses, some explosive, some silent. Their collective behavior, how often they blew, how often they fell back, and how they stirred and lit their surroundings, set the chemical thermostat that allowed the first low-mass survivors to be born. We read that thermostat today in thin, patient lines etched across the spectra of ancient stars. Certainty in astronomy is negotiated, not declared. Light from ancient stars arrives thin. Our instruments are finite. Models are imperfect. If the first chapters of the Milky Way are written in a few faint lines, we owe those lines honesty. This is the part of the story about error bars, where they come from, how they can mislead, and why a community determined to disagree constructively ends up more certain. Begin with the spectrum. A high-resolution rainbow is assembled from noisy pixels and overlapping Echelle orders. We correct the blaze, merge orders, and draw a smooth continuum so each absorption line is measured against the right baseline. Shift that baseline by 1% and weak iron lines change noticeably, especially in the crowded blue. Continuum placement is the everyday uncertainty. Careful tests with synthetic spectra and humans checking the machine keep it in check. Signal to noise is the second lever. For bright targets, we reach lofty S/N. For the faintest fossils, we accept rougher data. There are two main abundance strategies. Equivalent width methods integrate the light missing under a line. Synthetic spectrum fits reproduce the full profile. At low S/N, blends masquerade as single features and shove abundances around. That is why rare diagnostics like uranium demand hour-long integrations and why teams publish upper limits instead of wishful numbers. Assumptions about atmospheres matter just as much. A star's surface is not a flat slab, but a foam of convective cells. Standard one-dimensional LTE models treat it as static and perfectly equilibrated. Real stars are three-dimensional and sometimes far from equilibrium. For iron and light elements, non-LTE and 3D hydrodynamic corrections can shift key ratios by tenths of a dex at the lowest metallicity. Best practice is to report the simple 1D LTE results and the recommended corrections side by side. Interstellar space likes to photobomb. The CA-H-K lines used as metallicity flags are also carved by gas between stars. A narrow interstellar component can deepen a stellar line and fool quick pipelines. Sodium D lines and high-resolution profiles help separate the imposter from the real thing. Dust reddening is another quiet bias. If colors used to estimate temperature are off, every abundance that depends on temperature tilts with them. Modern teams lean on 3D dust maps to tame that slope. Binarity is a long game. Many metal-poor stars live in pairs. If a former giant donated carbon or S-process elements, an object can look primordial when it is not. Multi-epoch radial velocities catch many of these cases. SEMP stars wobble often, but not all. The best programs keep monitoring, sometimes for years, and update classifications when new motion appears. That slow discipline protects the fossil record from flattering imposters. Selection bias is the sneakiest trap because it starts before photons hit the detector. Photometric cuts that favor weak CAK lines naturally harvest carbon-rich stars whose CH bands are easy to spot at low iron. Avoiding crowded fields undersamples the inner halo. Bright time programs oversample the nearest candidates. None of this breaks the science if it is recorded. Publishing the selection function lets theorists impose the same filters on simulations, so apples compare to apples. Cross-calibration keeps the field coherent. Different spectrographs have different resolutions and wavelength coverages. Pipelines pick different line lists and atomic data. Laboratory oscillator strengths improve over time. Numbers drift unless anchored. That is why catalogs include repeat observations, standard stars seen by many teams, and transparent line lists with versioning. The goal is not to force one method. It is to measure and report the offsets so results remain comparable. Ages carry their own cautions. Subgiant clocks rely on distances and temperatures. Isochrones shift when stellar physics is updated. Astroseismology tightens ages for bright targets, but most ancient dwarfs are too faint for starquakes. Radioactive chronometers are powerful but delicate. Thorium and uranium lines are weak. Production ratios depend on nuclear physics, and blends hide in awkward places. Quoting realistic, statistical, and systematic errors matters more than a photogenic single value. Kinematics are only as good as the gravitational field you integrate in. Gaia gives exquisite positions and velocities, but rewinding an orbit needs a model for the Milky Way's mass, spiral arms, and growth. Over billions of years, small uncertainties compound. Dynamical associations remain probabilistic. Chemistry earns trust because it barely changes during a low-mass star's life. The multi-element barcode is the anchor when orbits blur. Now for the happy kind of uncertainty, disagreement as engine. Competing pipelines reanalyze the same spectra. Independent teams target the same dwarf galaxy. Groups publish both measurements and code so others can audit the result. Space missions add orthogonal constraints. ESA's Gaia nails distances and motions. NASA, ESA, CSA's James Webb Space Telescope measures dust and metals in galaxies at cosmic dawn. NASA's Hubble and ESA's Euclid tighten photometry and structure. When instruments built by different teams point in the same direction, confidence grows for the right reasons. There is wisdom in restraint, too. A spectrum with iron below detection is thrilling, but an upper limit is not a number. Publishing limits honestly and sharing null results when promising candidates prove ordinary prevents mirages. Those misses teach the algorithms what to ignore next time. Put the pieces together and the picture is robust by design. Uncertainties are not bugs. They are part of the signal. They show where the story is strong and where it is flexible. They point to the next best observation to make. The record we are building fossil by fossil, stream by stream, does not rest on one perfect star or one perfect model. It rests on many imperfect measurements that agree in the limit. That is how dim, noisy photons become a confident history of how the Milky Way learned to build. Next, we shift the spotlight from origins to outcomes. Once the universe learned to make heavy elements, how quickly did it start assembling rocky planets around long-lived stars? And could habitable worlds have arrived earlier than our own? The moment the universe learned to make heavy elements, a new game began. Dust could clump, pebbles could drift, planetesimals could crash and stick. In disks around newborn stars, millimeter grains snowballed into kilometer seeds, then into worlds. How soon did this start? The physics says, earlier than you might think. Once the dust-to-gas ratio crosses a modest threshold, the streaming instability turns drifting pebbles into dense filaments that collapse into planetesimals in a geological heartbeat. That threshold does not require sun-like metal levels. It needs enough, and the first supernovae and their dust forges supplied it locally. Observations back this up. Kepler taught us a simple rule. Small rocky planets form across a wide range of stellar metallicities, while giant Jupiters strongly prefer metal-rich stars. In other words, you don't need a gold mine to make a stone. Add ALMA's images of young disks, already ringed and clumpy, just 1 million years after they form, and the machinery looks fast once the raw materials are present. JWST extends the timeline outward, seeing dust and carbon-bearing molecules in galaxies that shone when the universe was still a toddler. The pieces for rock were stockpiled early. But rocky is not the same as habitable. A world can hold granite and still lose its air. Habitability wraps geology in a larger climate system, long-lived heat sources, a protective magnetic field, stable orbits, and a star that isn't constantly trying to sandblast the atmosphere off. Early on, many stars were red dwarfs, efficient for making planets but feisty in youth. Their flares and ultraviolet tantrums can strip atmospheres unless the planet's magnetic field is strong and the air is thick. Tidal locking piles, day on one side and night on the other. With enough air and oceans, the heat can circulate, but a thin atmosphere risks collapse on the dark. Water delivery is the quiet hinge. Disks start hot inside. Water ice lives beyond a frost line. If pebbles and planetesimals drift inward, they can salt rocky worlds with water. Too much, and you drown continents beneath global oceans that mute the carbon silicate thermostat. Too little, and you get a sterile desert. Migration muddles the recipe. A mini Neptune that wanders inward can stir the pantry and scatter ice, rich debris across the inner system, seeding just right worlds or wrecking them. The early universe didn't standardize this, it randomized it. So when could a truly habitable world, rocky, wet, with long-term climate feedbacks have emerged? A safe, conservative answer is, within the first few billion years, once multiple rounds of star formation had raised average metallicity and dust abundance, and once calmer, Sun-like and K-type stars were common. There are bolder ideas. Some theorists have pointed out that even a thin soup of metals and dust in the very first small galaxies may have been enough for rocky planets. Others have mused about an ultra-early habitable epoch, warmed briefly by the fading cosmic microwave background, a poetic thought experiment, not a plan for life. The sober middle ground is this: rocky planets likely appeared quickly in pockets. Truly clement, long-lived surfaces probably followed as the universe aged into a less violent neighborhood. If earlier habitable worlds existed, did life have a head start elsewhere? We cannot yet say. JWST's first atmospheric detections focus on puffy, hot exoplanets where signals are big. The road to sniffing air on a temperate, rocky world, carbon dioxide, water, ozone, methane, and balanced, non-abiotic ratios, runs through harder targets with smaller signals. Still, the path is real. Transmission spectra during transits, thermal emission on secondary eclipses, reflected light from future coronagraphs and starshades. Each step sharpens our sense of how common protective atmospheres are, how often water survives, and how stars sculpt the destinies of their planets. Closer to home, our fossils weigh in, indirectly. A halo rich in carbon-enhanced, iron-poor stars means carbon and dust were available early as coolants. Ultra-faint dwarfs show that rare R-process splashes can seed tiny ecosystems with thorium, uranium, and other heat sources that warm the insides of rocky bodies for billions of years. Even radiogenic heating is part of habitability. It powers plate tectonics, builds continents, and recycles carbon. The chemistry we read in ancient stars is not just a preface to planet formation. It sets the budget for the engines that keep planets alive. None of this guarantees that the earliest habitable worlds beat Earth to biology. Early galaxies were messier. Supernovae exploded closer to everything. UV backgrounds rose and fell. Gas flows were choppy. If fragile, nascent atmospheres were frequently blasted off and oceans were boiled away, the practical window for steady habitability may have opened later, favoring calmer, middle-aged K-dwarfs with stable light and generous lifetimes. Earth could be typical not because life is rare, but because conditions that keep life comfortable took time to settle into place. There's a humility test hidden here. We formed late enough may be the main requirement. Late enough for iron and magnesium to build cores and mantles. Late enough for potassium, thorium, and uranium to warm the crust. late enough for disks to keep their gas while still catching just the right drizzle of ice, late enough for a magnetic dynamo to run and for a star to calm down. The universe didn't need to wait 9 billion years for us, but it might have needed to wait for patience. So the answer to the headline, "Could habitable worlds have arrived earlier than our own?" is a qualified yes. The hardware likely existed, the climate software was harder. Somewhere, somewhen, a rocky planet may have opened its sky to a blue ocean long before ours. Whether that ocean lasted is the question our next decade of telescopes will chase. And that brings us to the last arc of our journey. We have met the fossils, the forges, the first stars, and the planets that may have followed. Next, we ask how to finish the map. Which surveys will fill the last blank regions? Which targets deserve the longest stares? And how do we build a final picture